So hopefully you have a good idea now of what each of those forms means. Right? Now, I'd also like to point out at this point that when you put a matrix into row echelon form, there are multiple different ways you can do it. Because you are able to swap rows, you're able to add different rows together. And so, there are a number of different ways you could put a matrix into row echelon form. So the point I'm making is row echelon form is not unique. If you do the same problem as somebody else in class, you could both get two different matrices and they could be correct. However, reduced row echelon form is unique. So if you're putting a matrix into reduced row echelon form, then you should always get the same answer as everybody else. All right? And we'll see how that works. Excuse me. Gauss-Jordan elimination, what I put up at the top of this page, is what we use to put a matrix into reduced row echelon form. So to put a matrix into row echelon form, we use Gaussian elimination. Then to put a matrix in reduced row echelon form, we use Gauss-Jordan, and it can be called Gauss-Jordan reduction or Gauss-Jordan elimination. They mean the same thing. I don't know why they use two different names for it. Anyway, row echelon form, Gaussian elimination puts a matrix into row echelon form. Gauss-Jordan reduction or Gauss-Jordan elimination, two different names for the same thing, put a matrix into reduced row echelon form. So, to do Gauss-Jordan reduction, you start, and I'll just make up a random matrix here, and I won't make it too difficult on us. You start by putting it into row echelon form. So the start of Gauss-Jordan reduction is Gaussian elimination. First step, make my zeros below the diagonal. Do zeros. There's a zero. That's good. We need a zero here. So we can I'll take row 3 minus row 1. Row 1 stays the same, 1, 2, 4. Row 2 stays the same, 0, 3, 5. And 1 minus 1 is 0. 3 minus 2 is 1. 1 minus 4 is negative 3. All right. We also need a 0 here. So we can take 3 times row 3 minus row 2. Gives us 1, 2, 4, 0, 3, 5, 0. 3 minus 3 is 0. Negative 9 minus 5 is minus 14. And we divide to make 1s on our diagonal. So we take row 2 divided by 3, row 3 divided by negative 14, and we get our matrix in row echelon form. 1, 2, 4, 0, 3, 5, or not 0, 3, sorry, 0, 1, and 5 thirds, and 0, 0, 1. Now what I've done so far is Gaussian elimination. Now here's the part that is different about Gauss-Jordan reduction, and that we don't stop here. We now want to get zeros up above our first one in each row. So we kind of go backwards. So Gaussian elimination, I don't know if it's a strict description of it, but you kind of work your way down making zeros. You work your way down the first column, make some zeros. And you start a little lower, and you work your way down, make zeros. But the Gauss-Jordan part, the part that comes after Gaussian elimination, you're kind of tracking your way back up from the right of the matrix over making zeros. So in order to make a 0 here, I can take minus 5 thirds times row 3 plus row 2. And I can take minus 4 times row 3 plus row 1. And I'm going to replace that, the rows 2 and 3 with those, or rows 1 and 2 with those results. So I just have minus 4 times 1 plus 4, that's 0, 0, 1, minus 5 thirds, plus 5 thirds, 0. And then finally, I need a 0 here, And so I take row 2, 2 times row 2, minus, not minus row 1, I don't want to take minus 2 times row 2 plus row 1. If I took minus row 1, this would become a negative 1, and we don't want that. And I get 1, and I have negative 2 plus 2, 0, 0, 0, 1, 0, 0, 0, 1. Okay, when you do Gauss-Jordan elimination, you will on a square matrix, you will always get 1s on the diagonal and 0s above and below the diagonal, which, for future reference, is called an identity matrix. And we'll talk more about what that means next time. So, if you have a square matrix, its reduced to echelon form is almost always going to be 1s down the diagonal. In a case where two of the rows are multiples of each other, which in a system would be where you get no solutions or infinitely many solutions, then you can wind up having like maybe a 1 here, a 1 here, but then this row might be all zeros or something like that. But for the most part, you will get 1s on the diagonal, 0s above and below. So you might ask, what's the point of this? Well, if we use this on an augmented matrix and to solve a system, then we'll have 1s on the diagonal, 0s above and below, but then we'll have some numbers down here, and we can just read off z equals whatever, y equals something, and x equals something. Okay. So I'll do an example with a system next. All right, so let's look at this system. First step is to write it as a matrix. Fill in my coefficients, 1, negative 2, 3, colon, 9, negative 1, that is a negative x, 3, 0, negative 4, 2, negative 5, 5, 17. Now, when we were doing solving systems, we had the freedom to eliminate whatever variable we wanted. When you put it in matrix format, you don't have that freedom anymore. You really need to eliminate these two entries and then this one and get 1s on the diagonal and so forth. So, if you were solving the system, you might go ahead and eliminate z from this equation, but when you're in matrix form, you don't do that. So we can go ahead and get rid of these. We can take row 1 plus row 2. We can take minus 2 times row 1 plus row 3. And we get 1, negative. The first row doesn't change. 1 plus negative 1 is 0. 2 plus 3 is 5. 3 plus 0 is 3. 9 plus negative 4 is 5. Negative 2 plus 2 is 0. 4 plus negative 5 is negative 1. Negative 6 plus 5 is negative 1. And negative 18 plus 17 is negative 1. All right. And our next step is to get a 0 here, which we can do by taking 5 times row 3 plus row 2. Our first row stays the same. Our second row stays the same. Our third row, 0. Negative 5 plus 5 is 0. Negative 5 plus 3 is negative 2. And negative 5 plus 5 is 0. Then our final step of the Gaussian elimination is to get 1s on our diagonal. We can take row 2 divided by 5, row 3 divided by negative 2. 1, negative 2, 3, 9, 0, 1, 3 over 5, 1, 0, 0, 1, 0. So we know right here that z equals 0, and this is where we would, if we were just doing Gaussian elimination, we'd say z equals 0, substitute, find y, and substitute and find x. But to do Gauss-Jordan reduction, we keep going. All right, we can take negative 3/5 times row 3 plus row 2. We can take negative 3 times row 3 plus row 1. I'm going to move over here. So, we have 1, negative 2, negative 3, that's 0. Negative 3 times 0 plus 9 is still 9. Then we have 0, 0 plus 1 is 1. Negative 3/5 plus 3/5, 0. Negative 3/5 times 0 plus 1 is still 1. And row 3 doesn't change. Then we want to get rid of that 2. negative 2, so we take 2 times row 2 plus row 1, which leaves us with 1. 2 plus negative 2 is 0. That's all the same. And here we have 2 plus 9, which is 11. And now we have a matrix, and this corresponds to saying x equals 11, y equals 1, z equals 0. So doing Gauss-Jordan reduction, this then is our solution. And 11, 1, 2 is the solution to that system of equations. So Gauss-Jordan, there's a little bit more to the process, but then you don't have to do the back substitution at the end. You just, read the answer right out of the matrix. So, two processes. Gaussian elimination gets our matrix in row echelon form. Gauss-Jordan reduction gets our matrix into reduced row echelon form. Both are ways we can use to solve a system. Remember that Gauss-Jordan reduction is Gaussian elimination plus a couple steps. So they're very interrelated.